Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation.
The researchers in the study reported in the paper titled, "Take it, Leave it, or Fix it, Measuring Productivity and Trust in Human-AI Collaboration," employed a mixed methods, task-based user study involving 76 software engineers. The participants were required to complete a programming exam with and without access to Google's conversational AI, Bard. The study aimed to observe the effects on performance, efficiency, satisfaction, and trust, depending on user expertise, question type, and measurement type. The task was a 10-question multiple-choice online exam on the Java programming language, divided into two sections, a Bard first and a Bard last section. Each section contained 5 questions, and the order of the sections and the questions were randomized for each participant. Participants had 2 passes at each question. During the first pass of the Bard first section, participants had access to Bard only. After selecting an answer, they could modify their answer with access to any non-LLM-based resources of their choice, categorized as book resources. During the first pass in the Bard last section, participants had access to book resources. In the second pass, participants could add Bard. The researchers constructed both an objective and self-reported expertise percentile rank within their sample. The objective expertise rank considered company internal statistics such as the amount of code written, tenure, Java experience, and previous readability exam experience. The perceived expertise rank considered participants' self-assessment of previous experience measured during the pre-task survey. In addition to evaluating descriptive data from the screening pre-task surveys and quantitative data from the exam using statistical methods, the researchers conducted a thematic analysis on transcriptions of in-session think-aloud commentary and post-task survey responses. Initial codes for this analysis were generated from prior research, pilot studies, and the first batch of participant data. The experimental work conducted to validate the methods in this study involved a mixed methods, task-based user study. The study observed 76 software engineers as they completed a programming exam with and without access to a conversational AI agent, Google's Bard. The study was designed to measure productivity and trust in human-AI collaboration. Participants completed a pre-task survey, then joined a one-on-one virtual, hour-long study with a moderator. They completed a 10-question multiple-choice online exam while sharing their screen and thinking aloud. Finally, they completed a post-task assessment. The exam consisted of 10 multiple-choice, single-answer questions on the Java programming language, divided into 2 sections of 5 questions each, a Bard first and a Bard last section. Section order and question order were randomized within subject. Participants had 2 passes at each question. During the first pass per question in the Bard first section, participants had access to Bard only. After selecting an answer, they had the option of modifying their answer with access to any non-LLM-based resources of their choice, e.g. documentation, search engines, loosely categorized as book resources. During the first pass in the Bard last section, participants had access to book resources. In the second pass, participants could add Bard, meaning they could modify their answer using Bard. The study constructed both an objective and self-reported expertise percentile rank within the sample. The objective expertise rank considers company internal statistics such as amount of code written, tenure, Java experience, and previous readability exam experience. The perceived expertise rank considers participants' self-assessment of previous experience, Java, LLM-based tools, productivity measured during the pre-task survey. In addition to evaluating descriptive data from the screening pre-task surveys and quantitative data from the exam using statistical methods, the study conducted a thematic analysis on transcriptions of in-session think-aloud commentary and post-task survey responses.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled, "Private Federated Discovery of Out-of-Vocabulary Words for Gboard," presents a method for discovering out-of-vocabulary, OOV, words in Gboard, Google's keyboard application, while maintaining user privacy. The method is based on federated learning and differential privacy. Federated learning, this is a machine learning approach where a model is trained across multiple decentralized devices or servers holding local data samples, without exchanging them. This approach is used to improve the vocabulary of language models in Gboard by discovering frequently typed OOV words on user devices. Differential privacy, this is a system for publicly sharing information about a dataset by describing the patterns of groups within the dataset while withholding information about individuals in the dataset. The system offers local differential privacy (LDP) guarantees for user-contributed words. With anonymous aggregation, the final released result would satisfy central differential privacy guarantees. Trie-based heavy hitters with local differential privacy, the algorithm discovers heavy hitters, frequently occurring items, by building a trie prefix tree layer by layer. Each layer of the trie stores a set of common prefixes of length corresponding to the depth of the layer. The trie is built in an iterative fashion starting from the root up to its maximum length. At each layer, users contribute by indicating one character after a common prefix from the previous layer. Moreover, randomization techniques with LDP guarantees are applied on each user contribution. Local dataset sampler, when a user's valid local contribution exceeds the contribution bound, the user performs local sampling to select a set of elements to report on. Two sampling methods are considered: greedy sampling, return the top elements that are contributed the most, and random sampling, return a uniform random subset of elements from the set of all contributed elements. Multiple pass algorithm, the algorithm can also be used as a building block for a multipass algorithm. The multipass algorithm builds multiple tries in a sequential order. Each trie is built by running the algorithm. After building each trie, the learned heavy hitters are added to the list of known words so that later runs of the algorithm will focus on learning new heavy hitters. To validate the effectiveness of the algorithm, the authors conducted experiments using the Gboard ENUS population. They aimed to learn heavy hitters within a pre-specified list of target words, Zen. Zen was kept within the existing known ENUS vocabulary to avoid learning sensitive out-of-vocabulary, OOV, words in undesirable parameter settings. Zen only contained words that were in the bottom 5% of user daily contributions, making the distribution of the words closer to the long-tailed distribution of OOV words. The authors measured the quality of the discovered words by computing an estimated coverage of discovered words. This was done by performing a counting task on Zen and obtaining the number of times that users contribute each word within a group of users. The estimated coverage of discovered words was computed by the total number of user contributions in the discovered set of words divided by the total number of user contributions in the entire target set. In the experiments, they set X to be string.printable in Python, which consists of single digits, upper and lower case letters, and other 38 special characters, 100 characters in total. They fixed max equals 10,000 in light of system constraints. They observed that the coverage of the target word saturates after a depth of 15, hence they fixed D equals 15 in their explorations. The authors also conducted a case study of OOV discovery in Gboard inputs. For OOV discovery in ENUS production population, they chose N equals 5 by 105, T equals 60, equals 10, D equals 15. They used greedy sampling as the local sampler and performed 2 passes to build 2 tries. The total number of users involved in the process was 15 million. They tested the coverage of the discovered words by computing the ratio between the number of OOV words in the discovered set and the total number of OOV words contributed by a test ENUS population. The result showed that the algorithm allows them to discover words that account for 16.8% of the OOV words.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled, Prompts as Programs, a Structure-Aware Approach to Efficient Compile-Time Prompt Optimization, introduces a novel framework known as Structure-Aware Multi-Objective Meta-Prompt Optimization, SAMMO, for optimizing meta-prompt programs during compile time. SAMMO employs a structure-aware approach to represent metaprompts as dynamic function graphs and uses a set of mutation operators to modify the structure and content of metaprompts. Metaprompt representation. SAMMO represents metaprompts as dynamic function graphs where each node in the graph has a function type and static parameters. The graph is recursively evaluated from the root node, enabling the representation of complex metaprompts. Mutation operators. SAMMO uses mutation operators, which are probabilistic functions that specify how to transition from a metaprompt to an edited version. These mutation operators can alter both the structure and the content of the metaprompts. Search algorithms. SAMMO provides two classes of search algorithms. If all mutators used are finite, then SAMMO can explore the space via enumerative search, either exhaustively, grid search, or by sampling search points at random search. When some of the mutators are infinite, SAMMO offers iterative search algorithms to optimize prompts. Specializations of SAMMO. SAMMO is a flexible framework that allows practitioners to mix and match search strategies with a large variety of mutation operators. The paper mentions several special cases of SAMMO, including automatic prompt engineering, APE, gradient-free instruction search, GRIPS, and syntax-guided task definition compression, STDC. Use cases. The paper demonstrates the effectiveness of SAMMO through several use cases, including instruction tuning, retrieval augmented generation, RAG, pipeline tuning, and prompt compression. In each case, SAMMO outperforms and generalizes existing methods of prompt optimization and compression. The authors conducted several experiments to validate the effectiveness of the SAMMO framework. These experiments were designed to test SAMMO's ability to optimize and compress prompts and to improve the performance of large language models, LLMs. The experiments were conducted across several use cases and involved various LLMs such as GPT-3.5, GPT-4, Mixtral 7x8b, and Llama 270b. Instruction tuning. The authors used 8 zero-shot big bench classification tasks that still had room for improvement. They compared SAMMO against other automatic prompt optimization methods like APE, automatic prompt engineering, GRIPS, gradient-free instruction search, and APO, automatic prompt optimization. The results showed that SAMMO consistently outperformed all other methods, regardless of the back-end LLM used. Retrieval augmented generation, RAG, pipeline tuning. The authors used 3 different datasets domains, GeoQuery, SMCalFlow, and Overnight. They used SAMMO with enumerative search to optimize exact match accuracy over a search space of size 24, trying out different data formats, number of few-shot examples, and DSL specifications. The results showed that SAMMO achieved substantial gains across most datasets and back-end LLMs. Prompt compression. The authors sampled 10 classification tasks with longer instructions, 1,000 characters or more, from the Supernatural Instructions benchmark. They compared SAMMO against 4 other compile-time prompt compression techniques, baseline prompt, APE, STDC, syntax-guided task definition compression, and stop words. The results showed that SAMMO achieved substantial compression rates, reducing the costs by over 40% while maintaining the accuracy of the baseline prompt. In all these experiments, the authors made sure to compare SAMMO's performance with other existing methods and demonstrated that SAMMO was able to generalize and improve upon these methods.
Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.